Now let's take a look at question 1. Get the region enclosed by the given curves and find its area. So this one. So these two curves, they're both parabolas. So start sketching. This x-axis, y-axis. And for the first one, you can find the x-intercept, that is 0 and -4. I mean, this one can be written as x plus 4, right? And it has two roots. First one is 0, the second one is -4. And its opening is upward. So it's kind of like that. Yeah, probably. And the second one, that is 6 minus x squared. So it passes through this point 6, so maybe here, right? Openings downward, something like that. Okay. So we see that the region bounded is this part. Okay. And then to do the integral, find its area, we need to use the upper curve to minus the lower curve. Right. So which one is the upper curve? The upper curve is this one. The lower curve is this one. Okay, this is the lower curve. It's the lower curve. And also we need to find the intersections, because that will be our lower bound and upper bound of the integrals. So to find the intersection, we're gonna let them equal. So set x squared plus 4x equal to 6 minus x squared, right? And I have 2x squared plus 4x minus 6 equals 0, which reduces to x squared plus 2x minus 3. And then I have x plus 3, x minus 1 equals 0. So this, it's -3 something, right? And this point is 1 something. Now we can write out the area. A is equal to from -3 to 1, and upper curve minus the lower curve. Okay, do this dx, and that becomes 6 minus 4x minus 2x squared, right, dx. And I will skip the computation. The final answer is 64/3, because I assume that you know how to do this arithmetic. I'm just basically, teaching you the idea. So that is question A. Draw out the upper curve, lower curve, and then the bounded region. Now let's move on to the second question. X equal to y squared minus 3y. So it's a parabola that goes sideways. This x, this is y. Okay. This can be written as y minus 3 times y. So it passes through 2 points, 1.0, I mean the y coordinate, 1.3, right? This opening is towards the right side, so it's like that. Okay, and y equal to x plus 3. The y-intercept is here, right? X plus 3. This is a straight line like that. Okay, so we can see the bounded region is this part here. If we use the integrals in terms of x, then we will have something difficult to work on, because let me enlarge this a little bit so that you can see it. Because if you do the integral in terms of x, then you will need to work with this part and that part, right? Because the integrations are different for these two curves. So it's kind of inconvenient if you do the integration in terms of x. So we will do the integration in terms of y, okay? And then we're gonna use the straight line to minus the parabola, because speaking of the x coordinate, the straight line is larger, because the straight line is kind of on the right side of the parabola when we think of the region. So the straight line is the upper bound and the parabola is the lower bound in this case. Okay, so we will do the integral in terms of y, but anyway we will need to find its intersections. This intersection is 0, 3. But what is this intersection? Now we plug in x into that equation to solve this thing. So y is equal to x plus 3, which means that x is equal to y minus 3. Okay, plug this x equal to y minus 3 into here. So we have y minus 3 equal to y squared minus 3y, which gives us that y squared minus 4y plus 3 equals 0. And it tells us that y minus plus 4, y minus 1 equals 0. So, oh no, y minus 3, y minus 1. Right, so y1 is equal to 3, y2 is equal to 1. So this point is something 1. Okay. Now do the integration to find out the area. Starting from the lower y, that is 1, and the upper y, that is 3, right? And we use the straight line to minus the parabola, because the straight line is on the right side of the parabola, and it's this region is, in terms of y, sorry, in terms of y I should use this x is equal to y minus 3, so it should be y minus 3 minus y squared minus 3y dy. Okay, that gives us this 4y minus 3 minus y squared dy. Now skip the computation, the final answer is 4 over 3. Okay, so and you can see that the difficult stuff lies on drawing the graph and figuring out in terms of which we should do the integral. Okay, so that is problem B. Now take a look at question C here. Y equal to 2 over x. Draw the diagram. Like that, right? Oh. Something like that. And then y squared equal to 4x. That's a parabola. Its opening is on the right side. So it's like that. There's a y equal to square equal to 4x. This is y equal to 2 divided by x. Okay, and we also need y equal to 1. So before I draw y equal to 1, I want to figure out this intersection so that I can get my y equal to 1 correct, its position correct. So what is this point? To know this point, I can plug in this y into here. Okay, so I will have 2 over x squared equal to 4x, which gives me that 4 divided by x squared equal to 4x. 4 cancel out, so we have 1 equal to x3, right? And then x is equal to 1, right? As is equal to 1, you plug in, you find that y is equal to 2. Plug in the y equal to 2 divided by x. So this point is 1, 2. After knowing that, I know where the position of my y equal to 1 is. It should be here, right? Y equal to 1, it should be here. It's lower than, slightly lower than that point. And that is the reason I compute this. If I don't compute this, I don't know where I should draw that y equal to 1, this straight line. Okay, y equal to 1 here. Now I can find my bounded region. It's here. Okay. Now we need to figure out in terms of which variable we should do the integration for. We should do that in terms of which one? In terms of x or in terms of y? Apparently in terms of y, because if you do that in terms of x, you will need to figure out this function here, right, and this function. They're two different functions, which is technically a piecewise function. You don't want that, so we do the integration in terms of y. And for that, we need to figure out which one is the upper bound, which one is the lower bound. In this case, the upper bound will be this one, It's upper bound. This one is the lower bound. Okay. Because it's in terms of y, it's like a scanning like that, vertical, horizontal strips here, like that. Okay, now we will use the reciprocal function, right, to minus the parabola, that is this one. It's x equal to 1/4 y squared. Oh, I did mistake again. In terms of y, I should write out the y expression. So I convert this one. That is x equal to 2 divided by y. Okay. So don't make the same mistake I did here. In terms of y, we should use the y expression. Okay, minus this and dy. Okay. And the lower bound of y should be 1, starting from the horizontal line. And the point we just figured out, that's 1, 2. So 2 is here. Okay. And skip the computation. The answer is, what is the answer? Look up the solution. The answer is complicated. That is 2ln2 minus 7 divided by 12. Okay. Now this is question C. Now let's work on question 2. This is a difficult question. So we need to draw the graph. The base of a solid S is a rhombus with the vertices, -1 something something, and the cross sections perpendicular to the x-axis are isosceles right triangles with one of the legs in the base. So what does that mean? It means that you have your base here on the xy plane. So imagine that you're looking from above. So this is the ground level, right? And you have your, my coordinate is ugly. Let me fix this. So your base is a rhombus having the vertices -1, 0. So it's here, right? It's 1, 0. 3 is here. -3 is here. This is just the base. And you're looking from above. And this is the projection on the ground level. Okay, ground level. And what does that mean by the cross section of the perpendicular to the x-axis or isosceles right triangle? So you have the triangle that is perpendicular to this xy plane, and when you look from above, it has the projection like this. So it's a how should I demonstrate? So let me draw this. That's the 3D version. This is x, this is y. This is x, this is y, this is z. Right? You have your rhombus like this. ground level. And the triangle is standing here, perpendicular to this XY axis. So it's like that. See that? You look from above, right? You look from above, and the purple thing you see is the projection. See? There's a purple, the purple leg there you see is the projection on the 2D XY plane. Okay? And since it's isosceles, so you see that this leg is gonna be equal to, and since it's isosceles, so you see that this leg is equal to this leg. Okay, so that's what this means here. And this small, slice of this piece of triangle, right triangle, is gonna scan through the entire base. So you have lots of these kind of pieces of triangle going from left to right, and it creates a solid S. So we need to figure out this volume of this solid S by doing the integration. So the idea is to find out the area of each small piece of triangle, this right triangle, and we're gonna add up these infinitely many pieces of triangles so we can obtain the volume. So it's like that. So we need to compute the area of the triangle, right? Area of triangle. And since it's isosceles, so the area, it's equal to 1/2 times the A square. A is the length of the leg, is A, right? And in this case, A is just 2y, right? Assume that this point is xy. We have A equal to 2y by symmetry. Okay? Because y is this is y, right? This is also y. So it's equal to 2y. How can we figure out what y is? Well, we can start with this. The equation of this straight line is green line here, right? It crosses the point 0, 3, and this 1, 0. This is 0, 3, right? This is 1, 0. It passes through these points, so we can easily figure out its equation, that is y equal to -3x minus plus 3. Okay, I'm not going over this again because I assume that you know this from 1500, how to figure out straight lines, how to find slopes. Okay, and then we now can express y in terms of x, right? Y is equal to -3x plus 3. Now we're gonna find the area. Area is 1/2 a square. A square is 2y square, right? So 2y square. Now plug in y, so that becomes that 2 times -3x plus 3 square. Okay, so it becomes this one. Now this is our expression, right, for the area in terms of x. And as I said, we need to do the integral. starting from left to and go to right in this way. So we can add up all the pieces of the triangles, add up their areas, so it becomes the volume. So now volume is equal to this from -1 to 1, okay, do the integration. And because of the symmetry, we don't have to do from -1 to 1, we can do twice of from 0 to 1, okay. That is also because if we do that from -1, then we need to figure out also this line. We don't want to do that, right? We don't want to really do that, so we use the symmetry to just saves us from doing that. So from 0 to 1, the area, right? Area dx that becomes this, plug in this area square dx, okay. And then skip the computation, find that the final answer is 12. Okay. Now we know how to do this question. And you see that the most difficult part is to figure out how to draw this diagram and how to use the integration to express this volume. And also there are some small techniques here, finding the area, finding the equation of the straight line. So that is our question 2, okay? Now let's move on to question 3. Use the Washer's method to set up an integral for the volume of the solid obtained by rotating the region bounded about a specific line. There's no need to evaluate the integral. That's very nice, right? Because computation is tedious. We want to demonstrate the idea, not the computation. Okay, so it's about rotation anyway. So now let's figure out the graph. We have the graph, this y, this x, right? 1 minus absolute value of x. So we know how to graph absolute value of x. It's a V shape, right? This is absolute value of x. Now what is negative absolute value of x? You turn that upside down, it becomes this. That's a negative absolute value of x. But we want 1 minus that. So you want to move it 1 unit up, just shift this thing 1 unit up. So it's like that. Shift this up. Okay, so it becomes now y equal to 1 minus. And I mean by drawing the graph is also from your 1500. So I assume that you've known how to do this. Just briefly mention to refresh your memory. And we are not going through in depth about how to do that. Okay, so that is our the graph here. And I also have y equal to 0. That is x-axis, right? The x-axis. So I have my region here, the region, this region. And we're gonna rotate this region about the x-axis. So you will see something like this. You rotate this, you get a cone like this, right? Basically a cone like this. And if my drawing is very messy, then forgive me. This is a cone. A cone. like this. Something like this. Okay. Now we need to figure out the radius when we do the rotation. The radius is the y. Okay. So you're gonna find your radius here, y, right? And the integration should be in terms of x, right? So you need to figure out the x coordinate of the intersection. This point here, that is easy. That is -1. This is 1, right? By letting this 1 minus absolute value equal to 0. Okay, so it's clear that the integration is from volume, sorry, is from -1 to 1, right? And we are adding up all these pieces of circles here. This infinitely many pieces of circle here. The area of the circle adding up equal to the volume. So for each small piece of this kind of circle, its area is pi r squared, and we know that the r is the y, right? So that becomes pi times 1 minus absolute value of x pi r squared dx, right? And to remove the absolute value, we have done something like this in our previous tutorial. We used the symmetry, right? That's twice of this, from 0 to 1. We don't have to go from -1 to 1 because of the symmetry. And from 0 to 1, x is positive, so you can remove the absolute value. And then do this and skip the computation. The final answer is, we don't have to do the final answer, right? Just express it. Okay, so it's nice. Okay, so that is how we do it. Figure out the radius and draw the graph and apply the formula, and also make use of the symmetry. Now let's work on question B here. Draw the diagram first. Y equal to 2 square root of x looks like this. And y equal to x is like that. And I also have the y equal to -1 here. So I have my bounded region like this, right? So rotation is about the y equal to 1, -1. So you have lots of things going around like this. Okay. Something like that. And you see that the inside is hollow, so we will need to figure out the radius 1 and radius 2 to do the subtraction. Radius 1 is this radius, purple radius, okay. Radius 2 is this orange radius. So radius 1 is the difference of the y coordinate of the square root function minus the y equal to -1. So it's 2 square root of x minus minus 1, which is 2 square root of x plus 1. Radius 2, it's the straight line, that's y equal to x minus 1, which is x plus 1. After having these two radius, we can start to work on the integral, but also we need to know the bounds. So we doing the integration in terms of x, right? And we're starting from 0 here, and we're ending at here. This point, to figure this out, we need to combine these two functions, right? Plug in this x here, so we have x equal to 2 square root of x, and it's easy to figure out that x is equal to 1 over 4. Is it 1 over 4? Well, what is the x? Square both sides, so x squared equal to 4x, right? X is equal to square minus 4x equals 0. X times x minus 4 equals 0, or equal to 4, not 1 over 4. Okay, so this point is 4. So now the integration gets from 0 to 4, and the pi r square, r1 square minus r2 square dx, which is pi times 2 square root of x plus 1 square minus x plus 1 square dx. Okay, so that is our question B. And because we may not have enough time, so I will skip question C and we will go maybe I'll go over question A here, the fourth question. Okay, it's already here. Use the cylindrical method. So firstly, draw the diagram. This is x, this is y, right? And this x equal to y plus 1 square root. We convert it to x squared equal to y plus 1, and move 1 to the other side, so x minus 1 is equal to y. So it's like that. It's a parabola. And x equal to 3, it's here. Y equal to 0 is the x-axis, so we have our region here. To use the cylindrical methods, we're adding up those so to use the cylindrical methods, we will need to figure out the radius of the shell, r of x, right? R of x here. Yes. This guy. That is just x, because we're rotating it about the x-axis, the y-axis, okay? And also the height is this one here. So that is just the y-coordinate, h of x, is equal to y, right? Is equal to y is equal to x squared minus 1. Okay, we have these things. And now it's clear that the integration is from this to this. So we need to figure out this point here. This point is obviously 1 because this is x squared minus 1, right? So the x-intercept is 1 here. And the other point here is 3. So integration is from 1 to 3. Now we can write out the integration from 1 to 3 2 pi rh dx, which is 2 pi. R is our x and h is our x squared minus 1 dx. And it's obvious, right? Not very difficult. Now let's move on to the last question. We have our y equal to this parabola. That is intercept -1 and 0, right? Just like that. Like that. Okay. This is the xy axis. And now we have also our y equal to -3 minus 3x, straight line, also passes through this -1, 0. So the straight line is like that. Like that. So you can imagine here, it's a very small bounded area here. Okay, that is not very nice, but I've tried my best. Now let's find the area, the radius of the shell. That is from here to here. So we know that the radius is the difference of their x coordinates. So it should be r of x equal to x minus 1. Yeah, absolute value. Right. Absolute value indicates the difference. And because in this case x is less than 1, because x is negative, so if you write x minus 1, it does not make sense. So it should be 1 minus x instead. Right? Because x minus 1 is negative. Distance here, radius, is always positive. So flip the sign. And we also need to figure out the height. That is r of x, h of x, sorry. That is the difference of the y coordinate, the upper curve minus the lower curve here. The upper curve is, in this case, -3 minus 3x. Lower curve is x squared plus x, which is negative x squared minus 4x minus 3. Okay, and we need to figure out the bounds for the integral. That is from this point to this point. This point is -1. We've known that, and for the other point, we need to combine these two equations. That gives us that x squared plus x equal to negative 3 minus 3x. And we have this 4x plus 3 equals 0, x plus 1, x plus 3, right? So this point is negative 3 something. So now it's clear that the integral is from negative 3 to negative 1 pi 2 pi rh dx in terms of x. And now we plug in everything. It's 2 pi r radius 1 minus x, and the height, that is negative x squared minus 4x minus 3 dx. Boom, that is the final answer. Okay, so that is our question B.